The next talk is a comparison between optimum path forest and K nearest neighbors classifiers. This is a work also for Unicamp. The authors are Souza, Lotufo, and Rittner. The speaker is Roberto Medeiros de Souza.
Good afternoon. My name is Roberto Souza. I'm a master's student at the University of Campinas. And I will be presenting this paper entitled A Comparison Between Optimum Path Forests and K Nearest Neighbors Classifiers. This is the outline of my presentation. Okay. K Nearest Neighbors was developed in the 60s and is still very used as a classifier in many problems, classification problems. And the Optimum Path Forest, OPF, was developed in the 2000s and has shown good results in many classification problems. KNN and OPF are non-parametric classifiers, simple to understand and implement. The motivation to develop this work is to study OPF properties further, since it's a new and interesting classifier developed by Papa and Falcão, which generalized the image forest transform to a supervised classification scenario. The IFT was successfully used in many problems such as image segmentation, boundary tracking, so we were really excited with the method for classification problems. And the second motivation is to show through simulations and theoretical considerations that OPF and 1NN are very similar classifiers. Here is the supervised classification problem formulation. We suppose that we have m different classes and any labeled samples, IID, independent and identically distributed samples. So the set Z is my set of labeled samples where X subscript is the futures vector and theta of X is the label of the futures vector. The problem consists in assigning new samples X to one of the m possible classes in a way to minimize the classification error. The optimal solution to this problem is known as the Bayes error rate and is achieved by using the Bayesian decision rule. But this optimal solution is only achieved when we have complete knowledge of the distributions, such as the classes distributions P of theta and the distribution of the features given the class. So it's more like a theoretical solution. We usually don't have those distributions. Okay, let's talk about the K nearest neighbors, starting with this simplest case, the 1NN overview. Suppose that we have 4 labeled samples, X1 and X2 from class blue, and X3 and X4 from class red. And we have a test sample represented by the green triangle in the image that we want to classify. So we compute the distance to each of the labeled samples and we'll assign the label of the nearest neighbor. In this case here, the nearest neighbor is X4, so this test sample would be classified as being class red. Okay, a mathematical formulation for this problem is the following here. We attribute to the test sample the label of its nearest neighbor, which is given by this expression here, where d of x, xi, is the distance between x and xi in the chosen matrix, such as Euclidean distance, Manhattan distance, or any distance. What is very interesting about one nearest neighbor is that we have a lower and upper boundaries for the error. It was shown by Cover and Hart in 1967 that as the number of labeled samples n tends to infinity in an m-class classification problem, the one nearest neighbor error rate is bounded by this expression, below by the Bayes error rate, which is the optimum solution, and above by this expression here that in the worst case is 2 times the Bayes error rate. The KNN classifier is a natural extension of the 1NN classifier, and it classifies X by assigning it to the label most frequently present in the K nearest neighbors. KNN takes into account K neighbors, so it's less sensitive to noise than one nearest neighbor. It was also shown by Duda and Hart that as n tends to infinity and k of the KNN also tends to infinity, the error rate tends to the optimal solution, which is the Bayes error rate. Okay, it's very interesting. We have lower and upper boundaries for 1 and n and k nearest neighbors, but we suppose that we have infinite labeled samples, which is not true. So it's more like a theoretical result. Here we have a 3 nearest neighbor anomalous case where we have 4 labeled samples. This would be the 1 nearest neighbor decision boundary, okay? And this would be the 3 nearest neighbor decision boundary. We can see that they are reversed, completely reversed. So clearly the 3 nearest neighbor doesn't have a good decision boundary. It's an anomalous case. So theoretically 3 nearest neighbors should be better, but in practice, not always. Here is how to improve this problem. We use the votes of the k nearest neighbors weighted by the inverse of the distance of each sample. Okay, the optimum path forest, I don't know if it's a very known classifier, but as I said before, it's an extension of the image forest transform. It introduces the notion of optimum path trees rooted in prototypes, and it has a structure that may support improvements both in time and accuracy performance of the classifier. Unlike K and N classifiers, we have a training phase, which we usually call OPF fit, and later the classification step, the OPF predict. The first step is we have a set of labeled samples, and we will represent it as a complete graph, where the weight of the edge is given by the distance between the samples in a chosen metric, and the second step is to compute the minimum spanning tree of this graph, as shown in this figure here. So we see in the minimum spanning tree the samples of different classes that are joined by edges of the minimum spanning tree. So we call these 2 samples here in the example prototypes, samples from different classes joined by the minimum spanning tree. So we can divide our set Z of labeled samples in prototypes, in the prototype set and the non-prototype set, as shown by these equations here. And also we have the OPF cost function. The goal here is to assign the test sample X to the prototype that offers the minimum path cost. And usually the OPF most commonly used cost function is given by this expression, which means the cost is the maximum edge in the path joining the test sample and the prototype. So replacing 9 in 8, we have the usual formulation of the optimum path forest problem. Here is the second phase, the classification step, OPF predict. Suppose that we have a new sample X that arrives to be classified, and so we have to compute all the costs to the prototypes. Here we have one possible path is X joining directly to X0, the prototype, so the cost would be 0.6. A second path would be going through X1 and then to X0, and the cost will be 0.5, which is the maximum edge in the path, and so forth. So also for the second prototype, X3, the cost will be 0.7 in this straight path, or 0.5 in the second possible path. And in this example, the test sample would be classified as being from class red, because this prototype offers the lowest path cost, which is 0.4, going through X2, X1, and X0. Here's the mathematical equation of what I just explained. And here we have an equivalence between 1 nearest neighbors classifier and OPF classifier. Let's suppose that we use all labeled samples as prototypes. So all test samples will connect directly to the prototype. So the path cost function would be exactly the distance between the test sample and the labeled samples in the classification. So replacing 13 in equation 11, we have exactly the 1 nearest neighbor mathematical formulation. So if we use all labeled samples as prototypes, we have OPF is equivalent to the 1 nearest neighbor classifier. Here's a simple analysis of the decision boundaries of OPF in 1 nearest neighbor. Here is the Voronoi diagram that shows the decision boundary of 1 year's neighbor, and here is the OPF decision boundary. The black edges represent the minimum expanding tree. The triangles are the prototypes, choose samples from different classes connected in the minimum spanning tree. And here in the third image, we have the difference between both decision boundaries. The green regions shows the difference between 1 year's neighbor and OPF. Points that fall in this region are closer to this sample here, but they would be classified as being from class red because the cost is given by the maximum edge in the path, that would be this. So this is the difference between 1 year's neighbor and OPF decisions. Let's go to some simulations. We perform simulations using OPF, 1 year's neighbor, 3 years neighbor, 5 and 7. In this case, we use the same weights as before, the inverse of the distance. We also use the percentile of the data sets used for training were varied from 20% to 50% with steps of 5. The features were scaled to the range of 0 and 1, and we use the Euclidean distance. Here are the datasets description. We focus a lot on bidimensional datasets because we want to see the decision boundaries. And these datasets here, Bolt, Checkers Board, Contours, Petals, Saturn, and Spirals are synthetic datasets, and Digits, Iris, and WBC are real datasets. So here is the illustration of the bidimensional datasets, Bolt, Checkers Board. We can see that they are very nonlinear distributions with some superposition, like in this Contours example, and the Petals. Saturn example also has some superposition, and the Spirals example very nonlinear also. Here are the accuracy results. We can see that, I don't know if you can see, but in red is the 1 year's neighbor accuracy, and in yellow is the OPF accuracy. They are very close to each other, with 1 year's neighbor always having a slightly better accuracy. Again, we can see that OPF and 1 year's neighbor have similar behaviors, and sometimes they even achieve better results than 3NN, 5NN, and 7NN. Here again, the same behavior, OPF and 1 year's neighbor. Again, these simulations, they are very similar, the accuracy results, with 1 year's neighbor always being slightly better. Let's see the decision boundaries that these classifiers achieve. Here we have the OPF decision boundary with the minimum spanning tree showed as black edges. Here is the 1 year's neighbor decision boundary. Here are their difference. We can see that they are very similar, OPF and 1 year's neighbors decisions, while 3 years neighbors, 5 years neighbors, and 7 years neighbors are completely different decisions boundaries. So here for the other data sets, the difference is not very high between OPF and 1 year's neighbors. Usually it's negligible, the difference. Again, for Petals datasets and Saturn datasets. And here for the Spirals case, which was a little bit more different here, the decision boundary, probably because of the prototypes chosen in the process. And here we have the real dataset results. We have, since K and N is less sensible to noise with K larger than 1, they usually achieve better results than OPF and 1 year's neighbor, as we can see here in the accuracy results. Again, for the WBC datasets, OPF and 1 year's neighbor are have worse results than K and N for K larger than 1. So the conclusions. It was shown that 1 year's neighbor and OPF are equivalent to each other when all test samples are used as prototypes. Simulations results and the decision boundaries analysis showed a similar behavior between 1 year's neighbor and OPF, but with OPF boundaries being smoother, probably because of the min-max cost function. The results obtained are not enough to achieve a general performance conclusion, but it indicates that OPF and 1 year's neighbors are similar classifiers, but OPF is a very recent one, and as shown in other papers, as I have the reference in the paper, it has a structure, the 3 structures that may may support improvements both in time and accuracy results. So, but what we say here is OPF and 1 year's neighbor are very similar classifiers in this formulation that we have nowadays. Future work propositions. We think that the method based on the minimum spanning tree for finding meaningful labeled samples to become OPF prototypes may be an alternative method for reducing samples in condensing nearest neighbors methods. Another possible investigation is implementing the KOPF, where instead of using only the distance to the nearest prototype to perform a classification decision, the distance to the K nearest prototypes are used and analyze if KOPF and K nearest neighbors with the same values of K, of course, present similar behavior such as 1 nearest neighbor and OPF presented as we shown before. I would like to thank CAPS and Unicamp for the financial support and of course you for your attention.
So there's any question?
So thank you for the presentation. I liked the way you compared both classifiers and also the nice figures that you drawn showing the decision boundaries. It's good for our students, for our lab to see how to visualize the data space and stuff, the feature space. I have a question. Can you return to the conclusion slide? When you say that it was shown that 1NN and OPF are equivalent to each other when all test samples are used as prototypes. Okay, that's one way of seeing things, but how realistic do you think is that? Because suppose that I have 10 million data points, and I don't want to use all of them as prototypes, and suppose that I only can use like 1% of this data to be prototypes. What do you think would be better, 1NN or OPF in that case?
Okay. In the usual formulation, we saw that OPF always was a slightly worse than 1 year's neighbors, than 1 year's neighbor classifier, and we showed that if we use all samples as prototypes, they are similar. So the higher the number of prototypes, the more likely are both classifiers. So that's what I'm saying. If I have more prototypes, more similar will be OPF and 1 year's neighbor. And I would use, in that case that you suggest, I would use 1 year's neighbor in the current formulation. But
yeah, I have another question. For 1 year's neighbor, you assume that you take all the distances between all pairs of data points in the training for the testing, right? So it's, if you have n points, you have n squared distances. Of course, it's symmetric, so you can discount, but you can see n squared things being carried to the testing. How does that affect the OPF, and what you can say about, here you compared the effectiveness of them, but how do you have something to say about the space used for both classifiers?
The space?
Yeah, because you need to, for k-niche neighbors, you need to store the whole matrix of every pair of distances, right? Because you need, if you have a new x point, you need to compare the distance, so you need all the matrix of computed distances. Do you also have that for OPF, right?
Yes, but in OPF, it was shown in another paper that you can, for processing time I'm talking about, that you can order the courses. You don't have to compare with every sample to know the best results, because you have in the tree structure that is very strong, so you can compare once, twice, and if the third one is bigger than the cost before, you can stop there, so you can improve processing time using OPF. It was shown in a paper by Papa, Falcão, and Suzuki, I think, in 2009. OPF is faster in classification, but in training phase, it's obviously slower because we don't have training phase in k-nearest neighbors.
Other questions?
Nice presentation. I agree with Anderson about the presentation. I think you showed very well. There are only a few considerations that I think you should take into account for for future works. One thing is that you always assume if you assume that the training set contains the same structure of the test set, right? Then this is one case where I believe that 1NN will be always better. One thing, there are two situations where I think OPF could make a difference. The OPF aims to detect chains in the data inside the class, right?
Yeah.
And I think those chains, they will be important to be exploited in situations where the training set is small enough to represent the test set. So you don't have enough samples, so you have only a few labeled samples that do not represent the structure of the data. So if you have that situation, and this situation is probably even very common in practice or when you have a higher dimensional data. And I'm curious to see a study similar to the one that you did, but for this situation. So this is a suggestion for a future work. So try to simulate a situation where the training set does not represent very well the test set.
Okay,
right?
I understand.
And this happens in practice when you don't have too many labeled samples. The second one, maybe even more important, is the fact that in many cases that when you, in practice, in image analysis, in several cases, the distance is not a metric. So it does not respect the inequality, the triangular inequality, right? This doesn't happen in your study because you use the Euclidean one.
Yeah.
So I guess this would be another situation that you should evaluate to see if under that condition, maybe you can find prototypes, some special elements in the set that make those chain connections, and those chain connections will never be found if you, because you're not using a metric, right? It's something different than a metric. So I guess these are the two suggestions that I have for you.
Yes, I understand. I showed that 1 year's neighbor is usually better than OPF, but only with Euclidean distance. Maybe if I change the distance, would be a little bit different. Is that what you're saying? No.
Yeah. What I'm saying is that in some practical applications, so the distance that you use is not a metric. It does not respect the inequality, the triangular inequality, right? So you should try that, for example, in some practical applications where you have descriptors with some distance functions which are not a metric, what happens? And the second one is when you don't have a good representation of the data in the training set.
Yeah.
Okay.
I understood. Here I focus a lot on bidimensional data sets because I wanted to show the decision boundaries. But I understand with higher dimensional in a higher dimensional problem, if I have not enough labeled samples in the start to perform on training, I understood.
Okay, let's thank the speaker again.